Hello children, welcome to the session 3 of the chapter Haloalkanes and Haloarenes. In the previous two sessions, we have seen the introduction, nomenclature and isomerism of haloalkanes and haloarenes. Today, in this session, we are going to see a very small concept. As I mentioned you in the previous class, we need to know about the nature of the carbon-halogen bond. As you people know, both haloalkanes and haloarenes have carbon-halogen bond. So it is very important for us to know the nature of carbon-halogen bond. Now, when you know the nature of the carbon-halogen bond, it becomes very easy for us to understand the chemical properties and the reactions of haloalkanes and haloarenes. As long as you don't understand the nature of the bond, okay, it doesn't, it won't be convincing further when you try to understand the chemical properties. Okay, so let us try to understand, okay, what is the nature of the carbon-halogen bond in haloalkanes and haloarenes, and we will see based on the nature of the CX bond, carbon-halogen bond, we can explain different properties of haloalkanes. Now, when you understand carbon-halogen bond nature, you can, okay, when you understand the carbon-halogen bond nature, then you can reflect on which properties. You can reflect on bond length property, you can reflect on bond enthalpy property, you can also reflect on the very important property which is your dipole moment, which is the direct reflection of the polarity of the carbon-halogen bond. Now, when we talk about carbon-halogen bond, what kind of bond it is it polar, non-polar, how to basically start understanding the concept of nature of carbon-halogen bond. Okay, let me try to explain in a very simple terms. I think most of you people know, if I am talking about carbon-halogen bond, halogen can be fluorine, chlorine, bromine, iodine, any one of them. Now, we know that carbon forms only covalent bonds. Okay, this is not a new thing you are studying now. In grade 10 and grade 11, you people already know carbon can form only covalent bond. Now, if we are thinking why does carbon form only covalent bond, you people know carbon has 4 electrons in its valence shell. So, carbon will always be in a confusion whether should I lose these 4 electrons so that I can get stability, or should I gain 4 electrons so that I can get stability. If carbon loses 4 electrons or gains 4 electrons, it will attain stability. Now, carbon in this confusion of losing 4 electrons or gaining 4 electrons, and you people know from your grade 10 knowledge, either losing 4 electrons or gaining 4 electrons, both of them are equally difficult. Now, looking at the difficulty of losing and gaining of 4 electrons, carbon prefers to share electrons. Now, when carbon prefers to share electrons, we clearly understand that carbon will only form a covalent bond. So, if I ask you about the nature of this bond, as you people know from your previous knowledge that carbon forms only covalent bonds, you can clearly tell me that, okay, if carbon is forming a bond with halogen, irrespective of what this atom is, as long as you know carbon can form only covalent bonds, you can confidently say that carbon will form a covalent bond with halogen or as such any atom, because carbon doesn't want to either lose or gain electrons, because either of them is very difficult. It prefers to share its electrons and form a covalent bond. Okay, this we have a lot of clarity that carbon would want to form a covalent bond, but the counterpart also should be wanting to have a covalent bond with carbon. Now, let us throw some light on halogen. Okay, let us throw some light on the halogen. Now, when I am trying to understand about halogen, you people know all the halogens are 17th group elements. When you know all the halogens are 17th group elements, when you already know that these are non-metals, you people are also aware of the fact that they need 1 electron to attain stability. They need 1 electron to get a fully filled outermost shell configuration. I am not going into the depth of outermost shell configuration and all that, because these are already learned things. So, I just want you people to recollect and remember that halogen needs to gain 1 electron so that it gets stability. Now, when halogen needs 1 electron to get stability, now halogen, if halogen had a metal with it, halogen would have preferred to form an ionic bond. But here, okay, which element halogen has in front of it? Halogen has a carbon element in front of it, and very well carbon will not form an ionic bond, so halogen has to negotiate only on the basis of sharing of electrons. Okay, halogen has to only negotiate based on sharing of electrons. Then what will halogen say? Okay, because halogen will say, okay, let us mutually share 1 electron. Okay, let us mutually share one electron. So carbon will come with one electron from its side, halogen also will come with one electron from its side. So what they will do, they will put one electron forward from each side. Okay, they will put one electron forward from each side. So now it is happy story. No, carbon has come with one electron, halogen has come with one electron, and both of them are sharing those two electrons. Halogen is also happy because now halogen has two electrons under its control. Because carbon is sharing this electron with halogen, now halogen has 8 electrons in its valence shell. So halogen is happy because now carbon also is at an advantage. It will think that okay, I need 4. It is fine. Halogen is sharing at least 1. So my hunger of at least 1 electron is satisfied. So both of them mutually will share these 2 electrons. Now, okay, halogen's octet is satisfied. Now halogen's octet is satisfied. Halogen is very happy. Carbon got a benefit of 1 electron from one halogen. If it other 3, it will take from some other atom. That is not our story. You already know that it will form 3 other bonds with hydrogens or any other atom it wants to. Okay, because we are talking about haloalkanes, we can very clearly say the other valences it can fulfill by taking a halogen, or it can fulfill by taking a hydrogen. Okay, that makes sense now. Okay, now okay, very happy story. Carbon and halogen are sharing 2 electrons. Everything is very good. But here you need to understand one important concept of electronegativity. Okay, here we need to know a very important concept of electronegativity. Now, you people know electronegativity is that is that periodic property where an element wants to keep the shared pair of electrons more towards itself. Okay, I'll give a small example. Okay, you and your friend are sharing the snacks. Okay, but you are little greedy that you want to eat more, then always you will try to put this. Okay, you both are there here, in between you have snacks. Because you are more greedy to have more snacks, you will always try to little bit pull that snacks packet towards you, because you are greedy to have it little more. The same logic you apply here. Okay, if an element is greedy to pull the electrons more towards itself, if it is highly electronegative, it will have more capability to pull the electrons more towards itself. Okay, this is from your periodic properties in your grade 11. Now, when I come to halogen, every one of us know, we have studied in grade 11 periodic properties, halogens are highly electronegative. Now, when we know halogens are highly electronegative, we have 4 halogens here on whom we are throwing light to understand different concepts. My 4 halogens are fluorine, chlorine, bromine, iodine. Okay, fluorine, chlorine, bromine, iodine. And you people know the electronegativity decreases down the group. Fluorine will be the most electronegative element. Okay, fluorine will be the most electronegative element. Keeping aside the fact that fluorine is the most electronegative element, on the whole, in the periodic table, 17th group elements, halogens are very highly electronegative. So, in place of X, if I put fluorine, chlorine, bromine, iodine, it is very clear that carbon has a very highly electronegative atom with it. Now, carbon, when it is there with a very highly electronegative atom, then this halogen is far more electronegative than carbon. Then what will this halogen keep on doing? This halogen will keep on doing? It will try to pull the electrons more towards itself. Now, when this is trying to pull the electrons more towards itself, this shared pair of electrons are more towards your electronegative halogen. Okay, are more towards your electronegative halogen. Now, when the shared pair of electrons are more near the electronegative halogen, usually covalent bond, none of them should get charges if the sharing is equally done. I'll give you an example. For example, if you take hydrogen and hydrogen, both the hydrogens are equally electronegative. So, the electrons shared by both the hydrogens will be at the center. None of them will be pulling it to their side. So, in this kind of cases, there is no possibility of any charge. Okay, there is no possibility of any charge because none of the elements have electrons. Okay, electrons very closer to them, they are equally shared. In this case, we don't talk about charges. Okay, because electrons are there at the center. But here if you see, due to the high electronegative nature of halogen, electrons are more towards this halogen. So here your halogen will get a partial negative charge and your carbon will get a partial positive charge. We don't take literally positive negative like you take in ionic bond. In ionic bond we take Na plus cation and Cl minus anion. I am not talking about literal cation and anion here. We are only using partial positive and partial negative because electrons are little bit more inclined towards halogen here. I gave it partial negative. Electrons are little bit away from this carbon, so I gave it partial negative. That doesn't mean that carbon has lost these 2 electrons and halogen has gained these electrons. No. Okay, they're still in between them, mutually getting shared, but little bit inclined towards one atom due to its high electronegativity. That is the reason I write partial negative here and I write partial positive here. Clear with this? So now why only one negative charge? Two electrons are there here. One electron is already belongs to halogen. So the extra how much it is getting right now? Only one electron. No? So that is the reason I have put only one negative charge. Okay, that is partial positive halogen, the electron which it already has, and the other electron which it is pulling. Okay, which is pulling. Okay, because these 2 electrons were supposed to be at the center. Okay, like this. So this is pulling even the carbon's electron more towards itself. Okay, that is the reason we have this partial positive and partial negative bonds. Now, when there is no possibility of any charge because there is no electronegativity difference, that kind of covalent bond I call it as non-polar covalent bond. Okay, that kind of covalent bond I call it as non-polar covalent bond. Now here when I am talking about, here this halogen is getting a partial negative charge, here you have a partial positive charge. Now in this covalent bond there is a possibility, we can clearly see there is some polarity due to the charges. So this covalent bond I call it as non-polar covalent bond. Okay, this covalent bond, what do I call it as? I call it as a non-polar, this covalent bond I call it as a polar covalent bond because here I am talking about partial charges. This bond becomes polar covalent bond. Here when you see hydrogen H2, electronegativities are same, so here we call it as non-polar covalent bond. So non-polar covalent bond is formed between 2 atoms which have almost similar electronegativities. A polar covalent bond is formed between atoms which have a difference, little, not a negligible difference, which have a pretty good amount of difference in their electronegativities. Then we talk about the polar covalent bond. Carbon and halogen have good amount of electronegativity difference, considerable amount of electronegativity difference. So here I call this bond as my polar covalent bond. So this is my polar covalent bond. If someone is asking you what is the nature of carbon halogen bond, that bond is your polar covalent bond. Now, okay, we understood that carbon halogen bond nature is polar covalent bond, which is due to the electronegativity difference between carbon and halogen. Halogen pulls the electrons little bit towards itself, creating a polarity in the carbon halogen bond. Now let us try to understand this table which is given in NCERT. Okay, based on the bond. Okay, this, if I take this bond, okay, because it can form bond with all the 4 halogens, CH3F, CH3Cl, CH3Br and CH3I. Okay, these are the 4 different kinds of bonds I have taken. Carbon is common among all of them. I have changed only the halogen part. Okay, I have changed only the halogen part. Now if I talk about the bond length, as you people know, if I take from fluorine, chlorine, bromine, iodine, okay, fluorine, chlorine, bromine, iodine. Okay, these are the elements in the 17th group of periodic table. As I go down the periodic table, what happens to the size? Size increases. So when I go from fluorine to iodine here, the size increases. Size of the atom increases. You people know, as we go down the group, okay, the number of shells increases, so the size also increases. Now if I go from fluorine, chlorine, bromine, iodine, the size increases. Now see carbon, this carbon size is fixed because here we have a same atom. The atom here is changing. So as the size of halogen changes, here from fluorine to iodine, the size of the halogen atom is increasing. Now when we know this, okay, if you see CF bond, okay, CCl bond, CBr bond, CI bond. Okay, you can see the bond length will increase when you come from carbon fluorine bond to carbon iodine bond. Now when the bond length is small, okay, when the bond length is small, the shared electrons will be under so much control of both the atoms. So the shared pair of electrons are under the control of the nucleus very strongly by carbon and fluorine, because the electrons are closer to the nuclei of both the atoms. Now when you come down, the distance between the atoms is increasing because the size of halogens increases. When you know that the distance between the atoms increase when size of halogen increases, when I come to Ci bond, the bond length is more, so the shared pair of electrons are not so much controlled by the nuclei of both carbon and iodine. So when the bond is not under so much control of the nuclei of carbon and iodine, it is very easy for me to break the bond. Now when it is very easy for me to break the bond, I need not use so much of energy to break the bond. I need not use so much of energy to break the bond, because to break the bond I need to give energy. To break the bond I need to give energy. So here I need not give so much energy to break the bond, because the bond is very weak, as the shared electrons are not so much controlled by the nuclei of both the atoms. So as we go down, when the size increases, okay, the bond length also increases, but the bond energy decreases when you come from carbon fluorine bond to carbon iodine bond. So if you see here the values of bond enthalpy of carbon halogen bond, okay, for 4 of them, okay, the strongest bond is seen in carbon fluorine, and the weakest bond is seen in carbon iodine, because as the bond length decreases, it is very easy for me to break the bond. So the bond dissociation energy has been decreased. So these are the orders of your bond length and your bond dissociation enthalpy. Now we'll quickly try to write them in the increasing and decreasing orders. Now when I take in terms of bond length, when I talk about the parameter of bond length, here what can I write? CHF bond length is less, okay, then comes my CH3Cl, then comes my CH3Br, then comes my CH3I. So this is the increasing order of the bond length. Now when I talk about the bond dissociation energy, CH3F will have the highest bond dissociation energy due to the less bond length. It is very easy for me to break the, okay, it is very difficult for me to break the bond, because okay, the bond between carbon and fluorine is very strong, because the shared pair of electrons are under control of the nuclei, because the shared pair of electrons are very closer to the nuclei of both the atoms. Then comes my then comes my CH3Cl, then comes CH3Br, okay, and then comes my CH3I. So I can say, what can I say from here? I can say bond length is inversely proportional to bond dissociation enthalpy. If you see from carbon fluorine bond to carbon iodine bond, the bond length is increasing, but the bond dissociation energy is decreasing. So these two quantities are clear for you. Now let me come to a very important quantity, which is my dipole moment. Before discussing the various values of dipole moment for these bonds, let us understand what is dipole moment first. Okay, now if you go back to the carbon halogen bond nature, we clearly know that it is a polar bond. Now when we talk about a polar bond in grade 11 in chemical bonding, you people have very clearly seen, when we are talking about a polar bond, there will be movement of electrons in the bond. Okay, because the electrons will be pulled towards the halogen, there will be movement of electrons. When there is movement of electrons, to measure the movement of electrons, to measure the polarity, we have a term which is called as dipole moment. Dipole moment reflects on the polarity of the molecule. Okay, now if I talk about dipole moment, how do we calculate? Dipole moment is a measure of polarity of any particular bond or any particular molecule. Okay, together the dipole moment of all the bonds will denote or will give the total dipole moment of the molecule. So okay, what does dipole moment indicate? Dipole moment talks about the polarity of the molecule or polarity of the bonds. How do you calculate dipole moment? Okay, we calculate dipole moment. mu is equal to q into d. You can, some books it is given it as d, in some books you see it as r, but ultimately what is d or r? D or r is the distance between carbon and halogen. D is the distance between carbon and halogen when we am talking about haloalkanes, and q talks about the charge. Okay, so when you multiply charge and the distance between the two atoms, then I get the dipole moment. Now, when I talk about the dipole moment of carbon halogen bond, if you observe the order of dipole moment here, first let me write the order of dipole moment here. If you see, dipole moment is highest for carbon chlorine bond, so CH3Cl. Then the next dipole moment is for carbon fluorine bond, then comes your CH3F. The next you have is your carbon bromine bond, and the next you have is your carbon iodine bond. So this is the data given for us in the NCERT. If we arrange accordingly, so this is the order, decreasing order of the dipole moment of carbon halogen bonds. Now we need to understand something here. Okay, now when we talk about the dipole moment calculations here, okay, charge plays a very major role here, because when you talk about dipole moment, charge is more dominating factor than the distance. Okay, charge always dominates over the distance factor. Now when we talk in that case, we people know fluorine is more electronegative. When we know fluorine is more electronegative, we expect CF bond to be more polar. Am I right? We expect CF bond to be more polar. Now as I come down, CCl, CBr, Ci, the electronegativity decreases, so the polarity of carbon halogen bond decreases. Now what can I write here? As I go from carbon fluorine bond to carbon iodine bond, as the electronegativity decreases, the polarity of the bond also decreases. So polarity decreases as I go down. So as the electronegativity of the halogen atom decreases, the polarity of the carbon halogen bond also decreases. Now, when we say that carbon fluorine bond is more polar, okay, more polar, it should lead to more charge, because the more polar the bond is, means what? Fluorine is pulling electrons more strongly towards itself. So the charge factor should be more in carbon fluorine bond. But surprisingly, when we see the order, we see that CCl bond dipole moment is found to be the highest. Now this is a very important question. Okay, this is very important question. Though the electronegativity of fluorine is high, and we also know that the polarity of carbon fluorine bond is more, but why is the dipole moment of carbon chlorine chlorine bond the highest? Okay, why is dipole moment highest for CCl bond? Okay, now when the question is why is the dipole moment highest for CCl bond, let us see and understand the reason behind it. Now when you take your carbon fluorine bond, when you take your carbon fluorine bond and when you take your carbon chlorine bond, yes, we do agree that carbon fluorine bond is highly polar due to high electronegativity of fluorine atom. But when you come to carbon fluorine, as you people have studied in the periodic table, from your fluorine belongs to second period, chlorine belongs to the third period. From second period to third period, if you observe, there is a very big jump with respect to the size. Okay, the size suddenly drastically increases. Now when I come to fluorine and chlorine, though fluorine is more electronegative, leading to more polarity of the bond, okay, which is expected more than this, but here the distance is very high. Okay, though the charge factor dominates in fluorine, but the distance factor, but the distance of CCl bond factor too much dominates. Okay, too much dominates the charge factor. Usually I told you charge factor is dominating, but when you compare CF and CCl bond, in CCl bond the distance factor is too much dominating, that what happens? Its dipole moment dominates the carbon fluorine bond. It's a very important question. Why is the carbon chlorine dipole moment more than carbon fluorine dipole moment? Though fluorine is more electronegative, it is due to the drastic increase in size of CCl bond, which ultimately increases the dipole moment of carbon chlorine bond. Okay, now if you see here for carbon chlorine bond, in Q into D factor, D predominates. Okay, D predominates over your charge factor. That is the reason which bond or which molecule has the highest dipole moment. CH3Cl molecule has the highest dipole moment, because carbon fluorine bond length highly dominates the polarity factor of the carbon fluorine bond. Okay, dominates the polarity factor of the carbon fluorine bond. Okay, you can write you can write it in very important bold terms here. Okay, bold terms here. In CH3Cl, the carbon chlorine bond length or bond distance predominates over the polarity. Okay, in CH3Cl, the carbon chlorine bond length predominates over the polarity. That is the reason you see the highest dipole moment for carbon chlorine bond. So these are about the different properties, okay, for haloalkanes, which we very clearly understood based on the nature of the carbon halogen bond. So questions are repeatedly asked on this concept. Now see, we try to cover everything regarding the nature of the carbon halogen bond. I want you people to understand one more dipole moment order here. Okay, that dipole moment order I want you to understand in detail because that has been repeatedly asked in the examinations. Okay, for that you should have a little bit understanding of the dipole moment in chemical bonding in your grade level. But even then, if you people forgot or anything, I will do that in detail. But for that, you should have a clear understanding of whatever I taught you people here. Okay, so let us see the dipole moment of halogenated methane. What is this and what is all? You can see this question as PYQ in many exams. So let us discuss that. This is a very important question where they ask the dipole moment order of monochloromethane, dichloromethane, trichloromethane and tetrachloromethane. Okay, this is a very important question where you need to know the increasing or decreasing order of dipole moments of these compounds. Before going to the dipole moment of these compounds, I want to tell you people one thing. Okay, dipole moment is a vector quantity. Okay, if you take here, dipole moment is a vector quantity, so it has a particular direction. Now when you are talking about dipole moment between two atoms which have different electronegativities, then only I can talk about polarity. Now the dipole moment is always shown from less electronegative atom to more electronegative atom. Okay, so because it's a vector quantity and it has a direction, the direction should always be from the less electronegative atom to the more electronegative atom, which makes sense because electron movement will be from the less electronegative atom to the more electronegative atom. Okay, now like this we will draw the dipole moment direction for all the bonds present in these molecules. Now if you see here, carbon is less electronegative, chlorine is more electronegative, so the dipole moment, okay, moves in this direction. Hydrogen is less electronegative, carbon is more electronegative, so the dipole moment is like this. Carbon is more electronegative, so the dipole moment is like this. Carbon is more electronegative, so the dipole moment direction is like this. Okay, here from carbon to chlorine electrons are going, so the dipole moment direction is like this. Here they go from hydrogen to carbon, less electronegative to more electronegative. Here also they go from hydrogen to carbon, here they go from carbon to chlorine. Okay, let me do for this. Okay, electron movement is from less electronegative to more electronegative, less electronegative to more electronegative, less electronegative to more electronegative, less electronegative to more electronegative. In the same way, here all the atoms are same, less electronegative to more electronegative, less electronegative to more electronegative, less electronegative to more electronegative, less electronegative to more electronegative. This is how I have shown the dipole moment direction for all the bonds present in these four compounds. Now here dipole moment basically goes on the factor of your vector addition. Okay, vector addition. Okay, now if you see here, I'll start doing from here. Here the dipole moment is going in this direction. Okay, here the dipole moment, all the dipole moments are going in the same direction. If you see, all the dipole moments are going in the same direction. Okay, now all the dipole moments are going in the same direction. Okay, now people might think that carbon hydrogen dipole moment might be little less than carbon chlorine dipole moment. It is true, but okay, all the dipole moments are going in a single direction, so the cancellation of dipole moments will not happen as everything is going in the same direction. So all the vectors they get added up. Okay, all the vectors they get added up. So in this case, the dipole moment will be highest because all the dipole moments of all the bonds are pointing in a single direction, so all the dipoles get added up. You can apply a vector addition concept here because it's a vector quantity. As all of them are pointing in the same direction, the vectors get added up and there is no cancellation as such, not so much cancellation. Because of the electronegativity difference of CH bond and CCl bond, a minute cancellation might be there, but no major cancellation I can see here within the vectors. So all the dipole moments get added up. So CH3Cl is supposed to have the highest dipole moment among all the 4 molecules. Now if you come to the next molecule, this is your, you can write the name also, it is your monochloromethane. Okay, this is your dichloromethane. This is your trichloromethane. This is tetrachloromethane. Okay, now if here if you see, okay, this dipole moment is going upward and these 3 dipole moments are going upward. Now this dipole moment which is going upward is cancelled by this dipole moment which is going downward. Now both are carbon fluorine bonds only, one is going upward, one is going downward, so these both get cancelled. Okay, these both dipole moments get cancelled. So ultimately, okay, my dipole moment is due to what? This HCl bond and this HCl bond. Okay, my dipole moment is due to this HCl bond and this HCl bond. Okay, my dipole moment will be due to this, okay, 2 HCl bonds, this HCl bond and this HCl bond. Clear? These two are not, okay, these two get cancelled out each other because they are equal and opposite. So okay, my 2 hydrogens, their dipole moment is going in the same direction. So my net dipole moment is due to 2 HCl bonds. My net dipole moment is due to how many HCl bonds? 2 HCl bonds. Okay, so next highest will be this. Now when you come to this molecule CHCl3, okay, this dipole moment is going in the, this carbon fluorine bond dipole moment is going in the upward direction. Okay, now this is going in the downward direction, this also is going in the downward direction. So this, okay, so this both, okay, this both going downwards will cancel out that. So my net dipole moment, see this hydrogen and this hydrogen carbon fluorine, if you observe this part, these vectors are getting added up. This hydrogen carbon fluorine, if you observe here, these vectors are getting added up. So my net dipole moment is due to one hydrogen chlorine bond, one hydrogen chlorine. So if you see here, from here to here, vectors are going in a single direction, so they get added up. Now this vector and this vectors, if you observe, they are opposite in direction, so they almost cancel out each other. Okay, so they almost cancel out each other. So the net dipole moment is due to this moment. From this hydrogen via carbon to this Cl, this moment is responsible for the net dipole moment, and only one HCl bond is responsible for the dipole moment. One HCl bond doesn't mean exactly HCl bond, means the movement from hydrogen to chlorine. The 2 movements from hydrogen to chlorine here, from this hydrogen to this chlorine, from this hydrogen to this chlorine. Here 1 movement from hydrogen to chlorine is responsible. So compared to here the dipole moment, net dipole moment will be less. Okay, net dipole moment will be less. Now however, directly writing this is more than this, I can write compared to this molecule, compared to dichloromethane dipole moment is less because here is net dipole moment is due to 1 movement, okay, from hydrogen to chlorine, okay, a movement of electrons. Okay, but here it is due to 2 hydrogen chlorine pathways. Okay, now when you come to tetrachloromethane, here your dipole moment will be 0. Here your dipole moment will be 0. You need not remember the dipole moment values for these 3 molecules. You just need to understand that it is decreasing in this way. Now why is the dipole moment 0? Because it is a symmetrical molecule. For symmetrical molecules, the dipole moment is equal to 0. Okay, if you don't want to go along with symmetry, you can see here, okay, all the dipole moments cancel out each other. This dipole moment is cancelled out by this dipole moment. Okay, so like that, all that, see, this dipole moment is cancelled by the other dipole moments because this dipole moment is going in upward direction and all other dipoles are pointing in the downward direction. So they mutually cancel out each other and you will not get any net dipole moment because all of them are carbon fluorine bonds and all the dipole moments get mutually cancelled, resulting in a net dipole moment of mu is equal to 0 and carbon tetrachloride is a symmetrical molecule. Clear? Okay, symmetrical molecule. So if I write the order, it is CH3Cl, greater than CH2Cl2, greater than CHCl3, and the least will be your CCl4. So this is the dipole moment order of these four molecules, and it is a very important question. No one mostly will ask you the reason for this, but you should know the order. Reasons no one will ask this. I have explained so that you have a clarity here. Here the net dipole moment is due to here the net dipole moment is more because all the vectors are getting added. Here these two are getting cancelled, so the net dipole moment is due to the motion of electrons from this hydrogen to chlorine and this hydrogen to chlorine. Next, here the motion of electrons is due to only one hydrogen chlorine bond because this dipole moment and this dipole moment will be cancelled. Here all the dipole moments are mutually cancelled, so the net dipole moment will be 0. So this is all about the dipole moment order of monochloromethane, dichloromethane, trichloromethane, and your tetrachloromethane. So this is all about your in detail understanding of nature of CX bond, and we have understood nature of CX bond, and we explained bond length, bond dissociation energy, and dipole moment of various haloalkanes using the nature of CX bond. This is a very important topic, especially for the MCQs. I try to put it in the easiest way possible. Hope you have loved the session. In the next session I'll be starting a very important topic, methods of preparations of haloalkanes. Till then, I'll see you till I see you in the next session. Keep learning, keep loving chemistry. Thank you. Bye.